All right, let's jump right in. We hear the term neural network thrown around all the time, right? It's one of the biggest buzzwords in tech. But what is it really? Today, we're going to get past the hype, pop the hood, and actually look inside the machine to see how it works.
Okay, so take a look at this. It's a 3. You knew that instantly, didn't you? I mean, it's a mess, it's sloppily written, it's super low res, but your brain has zero problem just getting it.
And that's the fascinating part, isn't it? Something that is completely effortless for us is unbelievably hard for a computer. No, seriously, stop and think about it. How would you actually sit down and write a program with a bunch of rules to define what a 3 looks like? A loop on top, a curve on the bottom. The variations are practically infinite. It's a nightmare.
And that's exactly where neural networks come in. See, instead of us trying to spell out all the rules, we build a system that can learn the rules on its own, just by looking at a ton of examples. And today, that's what we're focused on, the actual structure of that system. We're looking at the math and the logic that makes it all tick.
So, let's meet the star of the show. At its very core, a neural network is just a structure built out of layers. And it's this clever, layered design that gives it all its power. You basically have 3 main parts. First up, you've got the input layer. Its job is to see the raw data. So for us, that's all the pixels in the image. Then, in the middle, you have these hidden layers. This is where all the magic, all the heavy lifting and processing really happens. And finally, you have the output layer, which spits out the final answer.
Now, each of these layers is made up of things we call neurons. And you hear that word and you think, brain cells. But for what we're doing, it's way simpler. A neuron is just a thing that holds a number, specifically a number between 0 and 1. And we call that number its activation. You can just think of it as how lit up or active that neuron is.
So, for a little digit recognizer, the setup looks something like this. The input layer has 784 neurons. That's one for every single pixel in our 28 by 28 pixel image. The output layer? That has 10 neurons, one for each digit, 0 through 9. Whichever one of those neurons is the most lit up at the end, that's the network's final guess. But then you have these 2 hidden layers in the middle, the big question marks. What on earth are they actually doing?
So, what is the whole point of these hidden layers? I mean, why not just connect the inputs directly to the outputs? Well, the answer lies in this really beautiful idea. The network learns to recognize things by building up layers of abstraction. The hope, the grand idea, is that the network learns a kind of hierarchy. So the first layer, it just sees pixels. But maybe the next layer learns to recognize something more complex, like little edges or curves. Then the layer after that might learn to combine those edges into bigger components, like, say, loops or long straight lines. And that makes the final layer's job super easy. It just has to learn that, hey, if I see an upper loop and a vertical line, boom, that's a 9. Each layer gets progressively smarter, building on what the last one figured.
So that's the beautiful theory. But how does it actually happen? How does information get from one layer to the next? How does a neuron decide how lit up it should be? Let's get into the core mechanism.
Okay, so for any single neuron, it's basically a 4-step recipe. First, it looks back and takes the activation values from all the neurons in the layer right before it. Second, it calculates something called a weighted sum of those values. We'll get to that. Third, it adds its own special number called a bias. And finally, it takes that whole result and runs it through what you could call a squishification function, just to make sure the final number is between 0 and 1.
This brings us to the 2 most important dials we can tune, weights and biases. A weight basically decides how important the connection from a previous neuron is. Think of it like a volume knob. Some connections are really loud and influential, others are barely a whisper. The bias, on the other hand, is kind of like an overall threshold. It's a way of saying how high does that total weighted sum need to be before this neuron, really start to get active.
And that squishification function, a really common one, is called the sigmoid function. But its job is super simple and super important. After you add up the weighted sum and the bias, you could have any number. It could be huge, it could be negative. The sigmoid function just takes that number, whatever it is, and elegantly squeezes it down into that 0 to 1 range that a neuron's activation needs to be in. Okay, so that's the logic for one single neuron. Now let's zoom back out, because you have to remember every single neuron is connected to all the neurons in the layer before it. And when you start to put all of that together, the true scale of this machine starts to become, well, pretty clear.
In our so-called simple digit recognizing network, every one of those connections has a weight, and almost every neuron has a bias. If you add all of that up, you are looking at around 13,000 total parameters. That's 13,000 individual little knobs and dials that all need to be tuned just right for this thing to actually work.
I know, that sounds mind-bogglingly complicated, but here's another, simpler way to think about the whole thing. The entire network, with all its layers, all its neurons, all its 13,000 knobs, is really just one giant function. It's a machine that takes in 784 numbers, our pixel values, and spits out 10 numbers as the output. Yeah, it's an absurdly complicated function for sure, but at the end of the day, it's just a function.
So here we are. We've built the machine. We understand its structure, the layers, the neurons, the weights, the biases. We know it has 13,000 knobs that we can turn. But that brings us to the biggest, most important question of all. How do we teach it which way to turn them? How does a computer possibly figure out the perfect setting for all those thousands of knobs just by looking at data? Well, that process, that's called training. And that's a story for our next explainer.